Hello, one. Okay, it is on. Good. That was a great lunch. Wow. One thing that I'll mention now is that all the presentations that we get here this week, we intend on putting up on the EME newsletter website somewhere for download. So, you know, it'll take a few weeks to get it up there once we all get settled back at home, sort of thing. So you want to take all those notes for all those details, and you'll be able to get it then. So. Our next presenter is well known. I probably don't even need to introduce him. Paul W1GHZ. You know, he's been a serious microwave experimenter for years, and he's published numerous articles, just great stuff. He's the owner of the W1GHz microwave antenna book online, which I know is just a Bible. It's just wonderful. So, and the projects that he's published, I mean, they're easy to do. They're reproducible. Great people have great success. I've seen a lot of pictures of his stuff here in the EME group. So I mean, it's just fabulous material that Paul has been producing over the years. So please welcome Paul Wade, W1GHZ.
Buenos dias. Is that what you say? Okay, that was a really good lunch, and you can all fall asleep now. I would if I weren't standing here. So if you notice me limping around, I postponed my knee replacement so I could get here, and I'll be getting it in a couple of weeks. So. But at a recent conference, someone said, "Boy, thank God for modern medicine." And someone else said, "Without modern medicine, there'd be no ham radio left." So, I'm going to tell you about large IMU feeds for improved G over T on offset dishes. So now that everyone's switched to solar cookers, and they are expensive. That is the most expensive dish I ever bought. At $80. Somehow, you know, I've come home from a weekend and found an 8-foot dish lying in my driveway. Present from someone. My wife was impressed. What's that?
You didn't order it for sure.
Okay, so if you're going to do a solar cooker, you can also use it as a 47 gig, or you don't have to go quite that high, but it's also a good feed for a cast grain dish on your solar cookers. We'll see later. And somewhere here, I'll pass around a couple of feed horns so you can see what they look like. We were going to bring a 10 gig one, but thought security might have a little problem with this aluminum cylinder in the suitcase. All right. So I'm sure you've all seen this W2IMU feed. Take your waveguide, flare it out at the right angle, and a bright length horn there, and you get a dual mode feed that has very low side lobes. This was invented by Dick Turin, W2IMU, and he patented it, and he probably hasn't renewed it. So, dual mode horn, we have your normal TE11 mode. This is showing vertical polarization, because if you're simulating antennas, you always put the H field vertical, or the E field vertical, sorry. And you add a TM11 mode, that's what the flare does. And notice that where this is minus, this is plus, and vice versa. So the currents in the rim cancel, and you get rid of all those side lobes. Much easier than on a Yagi. Okay. So yeah, we put T11 mode in the input, flare generates the other mode, and they travel in different velocities in the horn, and at some distance they cancel. Get no currents, reduce side lobes, and you get more power on the dish and less ground noise. What more could you want? So, the one that everyone used for years was the original one, 1.3 wavelengths in diameter, but Dick also described a much bigger one, and which has a narrower beam width, and excuse me, and that's what we're going to talk about today. But any wavelength from 1.22 up to about, which is the smallest the TM11 mode will propagate in, up to about 2 wavelengths in diameter, and beyond that, there must be other modes because the pattern goes to hell. I think that's the technical term. Oops, yes. So the horn length increases with larger diameter, and the flare angle in the paper decreases with larger diameter, but we'll get to that. So years ago, I made a couple using precision fabrication techniques. Found a couple of pieces of large copper tubing somewhere and soldered them up. And that actually worked quite well. And I used one of them on my periscope antenna for many years. So, but now I have access to a CNC machine, and was able to machine some aluminum ones for 10 gigs. And you can see the smaller one is fairly long, and the larger one is very long. Now, if you've ever run a lathe, you know that to make bore a long cylinder without a lot of chatter takes better technique than I have, and that's on a CNC machine. So anyway, this is all based on simulation, and that's just a computer game. So measurement. Measurement is hard at high frequencies when we're playing 47 gig, but scale it to 10 gig, we can machine fairly accurately at 10 gig. And there's several aluminum pipe sizes available for 10 gig. And the way we were making the higher frequency ones was with a center drill with a 30-degree angle. So resimulated with a 30-degree flare rather than the exact one specified by the equation. And with a little adjustment of the length, they work quite well. So I made several with different ranges of feed diameters and measured sun noise. Now we have something meaningful, not just a computer game. So machining them, yes. So they're around 50 millimeters in diameter at 10 gigs, 100 millimeters long. Yeah, that's 4 inches. Yeah, around 4 inches long. And boring it from solid stock is wasteful, and in the last year or so, not only wasteful, but damn expensive. Aluminum has gone out of sight. So it's priced like copper used to be, and copper's priced like silver used to be. So taking expensive aluminum and dumping most of it on the floor is not only hard, but very expensive. So we'll get back to that. So rather than bore the whole thing, after it didn't work, machine just the flare section and the input. So it's just an angle on a short piece of small diameter. And then turn it down to fit inside some stock pipe. And you gotta get it within about a tenth of a millimeter, because what I'm gonna do at the end is, heat up the pipe enough so it expands and fits over the flare section. And as soon as you do that, it all cools off and that's on there permanently. It's now one piece of aluminum. But to get that tolerance, I found the hard way that after machining it, you go have a cup of coffee while it cools off, because the dimension changes that much coming off the tool. It also feels hot. So, here they are. The original small one, that's about 1.7, 1.6 wavelengths diameter, and that's almost 2 wavelengths, and that's in between. And to match them to a waveguide, WR90 is a matching section there. And Jeff, Jeffrey, WA6 KBL, did the original design on that. So G over T, anyone need the full explanation? Read the equations. Gain is good, noise is bad. G over T. So here's the original small one. A lot of people use these on offset dishes. They're really good, about 0.5 F over D. And you can see the G over T curve peaks way down there at the about your solar cooker F over D. But the efficiency is kind of way down there, so you don't really want to use it for the cooker unless you're just looking for low noise. Maybe radio astronomy. You wouldn't do that on a solar cooker. Small. Okay, if you go to a larger one, and it's better at a larger F over D, good for a offset dish, and the SG over T is moved way up, and it's still pretty good. Somewhere here is a compromise with the offset dish. So, and of course, I don't have to explain to all of you that you get great G over T if you don't have a preamp, and it goes down in a hurry with your noise figure. Every 10th of a dB up here drops you a dB in signal to noise for G over T. So let's see. Start here at the raw antenna. You put that right angle connector in with a little piece of coax, and you're down to your preamp here. 10 gigs, use a waveguide relay and waveguide input. Preamp straight through, nothing but air in the way. You get a lot closer to your preamp. But you won't know that. No, you don't, because there's still people using coax. Okay, so sun noise and ground noise tells you your G over T. Hot sun, cold sky, gives you an idea what works. And measure your preamp, ground noise compared to cold sky. You know what cold sky is, you know what the ground is, more or less. About 270K when I did it. You know what that means. You won't get that here in Tenerife. Okay, so I did this with my W3T preamp. They claim 0.6. I get about 0.75, but I can't. I've still got some spillover. And to measure sun noise, thanks to Mario. Total power program is wonderful. .0 NAA, an expensive dongle. And so let's see, $30 for that, and $129 for the laptop. That's about as cheap as you'll get for a U over T. That is not a high power motor. And what I do is just peek up on the sun. You can see me fiddling around here trying to find it. Peek it up, and then let it just drift off. Down to, so it's not that point in Leo, but at 10 gigs, the sky's pretty cold everywhere. So that's the technique. Sometimes there's a big jump here. Oh, shit, there's a cloud went over. You can detect that. All right, so here's just measuring the feeds for sun noise. And if you read one of the original Crawford Hill EME notes, he says, measure your feed horn inside a dish. Limit the ground noise you're picking up. Guys with 10-meter dishes, you get really good shielding. 1.2 meter helps some. But I can tell the difference between putting the dish under and not. Here it is. So what's this? Yep. Sun. Looking for cold sky and casting past something, and then there's the ground noise. Which obviously on a much smaller system. Oh, that's just the preamps. Okay. Just the feed. That's the sun noise on the feed. Cold sky, ground noise. Roughly what I measure. Did I go backwards? So here I am in this elaborate setup. One thing, first thing you do when you're measuring sun noise is take a step attenuator and make sure you got some headroom above the noise floor and below the skies. Some preamps have a whole lot of gain, so you don't want to saturate it. You need about 10 dB of headroom on the upside. Gaussian noise is not constant, it has high peaks. And on the low side, you just want to get above get a few dB above the background noise. All right, this is my little portable system. There isn't a whole lot of sun noise. It's not very preamps, coax, but you can pretty well tell it's working. You can even see the sidewalk. All right. And when nothing's working, what I do is here's the feed horn. I take another feed horn and just hook them into each other and measure the noise figure on the meter or the power, output power on the meter, and allow a dB for this fancy connecting together. For a quick test indoors, when it's raining or snowing, it's a good way to make sure things are working. Okay, so now we get to the feeds on the dish. So I did it on my 1.2 meter dish and on a 1 meter dish, just to make sure things all scaled. Wasn't a problem with either dish, because these came from the usual sources, somewhere. And you might notice that I have it mounted upside down because it made it easier to get pointed that high. So again, 4 feeds, big, nearly as big, pretty big, and small. There's a big one. Nice clean pattern. Tiny little side lobes, 30 dB down. I think if you fiddle the angle on, the flare angle on the feed, you could knock that down a couple more dB. Makes cutting a larger taper, and that's not fun. Okay, so, see, good efficiency. Expected, I'm gonna put the GOT on this one. Good efficiency, and we know the GOT is compromised somewhere. And sun noise. So it's on the neighborhood of 11 dB on a 1.2 meter dish at some SFU. Which I thought was pretty good when I heard people were getting 9 dB on their 1.8 meter. I thought that was good. So, the next smaller one, again, good pattern, small side lobes, and peaks at a slightly lower F over D. We're going to notice is the small ones, and I can't guarantee this is nothing drifting. The smaller ones seem to give a slightly higher noise floor. That's where the T coming up more than G coming down. 0.6 meter in pattern, small side lobes, slightly lower F over D. And that's slightly lower sun noise, mostly at this end. Since then, no, this is the original 1.3, and it's slightly lower efficiency, much lower F over D for an offset dish, and quite a bit lower sun noise. Now, so there's the patterns. Narrow, wider, wider, wider. Okay, here's the comparison. What I measured on different days, not consecutive days. Next bigger one is a little less. The next bigger one is a little less. And small one is down quite a bit. And then, so that you didn't just believe I was making up numbers, I sent one off to Barry. See, full waveguide system. And Barry said it was half a dB better than any of his best ever. EME feeds. Here's what he sent me. He's getting 2.7 dB of noise, moon noise on a 1.2 meter dish.
2.4. 2.4.
Oh, 2.4, I'm sorry, yes, that would be exceptional, wouldn't it?
Yes.
Okay. And the sun noise is about 12.5 dB pointing into the bushes. So, very lucky. I got a friend who's a really good machinist to make up a couple of 24 gig ones. So, and Barry looked at one. He was measuring 15.7. He's now measuring 16 dB of sun noise on 24. So, and moon noise 2.4 dB, better than before. And that's with normal summer conditions in Manitoba. 55 degrees.
For Texas.
Yeah. 55 degree F.
Never.
Okay. Oh, that's Texas, yes. That's LUA. Is that Barry on there? Barry hit it 24. I guess he was getting good. And Al also measured, so he says it's top performer. So there we go. On offset dishes, the biggest one at the best G over T for terrestrial, for your portable station. Any of those are good. And if you can find one that my dual band feed, it's pretty good too. But, you know, for anything other than the EME, whatever gets you on the air. You know, the tends count on it. The tends count on EME. They really don't. Most of the time, I'm not. So construction, machining it on CNC lathe with a long boring bar, and watching it run is pretty boring too. It's very, very difficult to machine with a good finish. In two-piece, you have machine the flare and fit the tubing over it, heat it, shrink it on, very tight tolerances, and the tubing does not have that tolerance. So there they are. So affordable feed points. Having somebody machine one of those is going to cost you a lot of money. Having less than 50 of them made would cost a fortune, and then they go into expensive. So instead, we've been looking at a two-piece feed, 8 and 9 tight tolerances. But what about 3D printing? Well, Don, W1FKF in the back row, is really good at 3D printing. So we've been working together on this project. We started with Carl at EME2024, made these plastic horns. And he gave me one, and I took it home and did a really crappy job of lining it with copper tape. White copper tape. He's sold his guitar tape. And apparently, when you use 1950s technology in your electronics, and you need to shield it. I don't understand. Anyway, so first test, it was about 0.6 dB down from the same size one. For something a lot easier to make, that's not half bad. And then Don printed a full born, nicely done, and he lined it much more carefully than I did. And it worked about the same. He said, well, what if with the copper on the outside? That would be much easier to make. Unfortunately, the plastic on the inside does not help. So, you know, there might be other plastics that are even worse, but probably not many that we can afford that are much better. So Don said, what if we didn't make any cylinders? Just printed the flare and use a metal tube input and the water pipe for the input and aluminum for the output, and tape over the whole thing on the inside. Okay, there we go. So first I think I had some brass lying around. We tried that. That seemed to work okay, and then we priced brass. Remember I said about copper being expensive? No. So, yeah, we made one old water pipe. That's really expensive and heavy, not circular. Structural tubing is not any better. But then one of us found they had for intercooler intake tubing. I don't know if they do hot rods in Europe, but people like to fancy up their V8 engines and get 3 million horsepower out of them. And they make these reasonably priced aluminum tubings that are really nicely made. There you go. 2 pieces, 51 millimeter diameter for $23. That would be 40 euros in Europe. Anyway, nice finish, nicely circular. And they come up to, this one comes up to 3-inch diameter. So, if you're looking at this, beware of the ones that are chrome plated. Chrome is a very excellent attenuator at RF. So, here's one with the aluminum tube output, the printed flare section, and the copper tubing input, and this one we just put a SMA connector on to test. Okay, now, as I said, they come up to very large diameters. 3.5 inch is about the right size for 6 centimeters. There you go. So you could use 2-inch aluminum here. It actually has a thick enough wall to mount an SMA connector on, and a 3.5-inch, so it's 170 millimeters, somewhere around there. Anyway, oh yeah, I put a millimeter rule there so you see what it is. And Don said, well, we could put a cassegrain on this, feed the solar cooker. Not have to have that thing hanging out there. And 3D print the sub-reflector. Put copper tape on that. And Bob's your uncle, right? All right. So I guess I'm summarizing. The large IMU feeds are good for offset and cassegrain dishes. Hard to machine. Oh yes, for higher bands. That's what I'm talking. Yes. So micro mooring bars are very expensive and break faster than you can blink. And the calculated flare angle is about 25 degrees, but long center drills come with 30-degree angles. So that's when I originally started fiddling with the flare angle. And for not much money, you can buy a whole set, good for several different bands. Like the 47 gig one that went by. Here's a cable up to 241 gigs. We've made all of these. I have not successfully made a 241 yet, but we're working on it. Again, cassegrain 47 gig, that's the little horns. Sub-reflector, that one's actually in metal. We still 3D printed them. Oops, not pushed storm. Here's one Don made for 78 gigs. Same, I machined the sub-reflector, he did the above parts. 122 gig, that's just your Chivo Edmonds solar reflector. Small solar cooker, if you like. So, in fact, they're all solar cookers right here. Oops, did I screw up again? I rushed it. That's the last one, that's why it stopped.